A golden, flaky exterior might look ready for a bakery window, but that crisp outer shell often hides critical structural failures. To truly judge a croissant, the outside is largely irrelevant. The interior crumb is the only honest record of what happened on the prep bench. A flawless execution yields a specific internal architecture. You are looking for uniform honeycomb cells, stretching evenly from the center to the crust. Notice the thin, unbroken lines of dough. They completely encapsulate wide, irregular alveoli, ensuring every pocket of air is trapped and distinct. When the lamination process breaks down, those delicate structures collapse into a compressed, dense mass of crumb, where the layers have simply fused together. You'll also see irregular, random tunneling cutting through the dough, often leaving a heavy, greasy sheen on the interior surfaces. Once the physical structure of these layers is damaged during rolling, it is strictly irreversible. You cannot repair a shattered lamination in the oven. By reading this cross-section as a diagnostic map, a baker can trace a dense, greasy bite directly back to an invisible physical error made hours earlier. Proper lamination is a balance of three variables: steam, fat, and gluten structure. The butter itself serves as a continuous physical barrier. Its only job is to keep the individual sheets of dough separated. Notice the alternating bands of dough and butter. As oven heat hits, water trapped inside the butter vaporizes into expanding steam. Meanwhile, the gluten network provides flexible walls around that steam. It stretches to contain outward pressure without tearing. When this happens across hundreds of layers at once, the result is oven spring, a simultaneous, uniform vertical expansion. Without perfectly continuous sheets of butter to generate and trap that steam, a dense block of raw dough has no mechanism to lift itself into an airy honeycomb. The preservation of those layers comes down to preparation, and the most common point of structural failure is always temperature. If the butter is too cold, it loses its flexibility. Under the pressure of the rolling pin, the solid fat fractures and shatters into fragments instead of stretching into continuous sheets. Conversely, if the butter is too warm, that same mechanical pressure simply blends the fat straight into the dough, destroying the physical barrier entirely. For optimal temperature zones, butter must sit perfectly between 14 and 16 degrees Celsius to stretch without breaking. But the dough needs to remain distinctly colder, between 4 and 6 degrees Celsius, preserving a firm structural integrity. This specific temperature gap achieves perfect equal plasticity. Despite being 10 degrees apart, the butter and dough must yield to pressure with the exact same physical consistency. Even with perfect temperatures, the mechanics of rolling carry heavy risks. Too much downward pressure blindly compresses delicate layers, crushing steam channels before they even form. Skipping rest periods is equally damaging. As the dough is worked, the gluten tightens. If pushed too far, that tension physically tears the dough sheets apart from the inside. Building the structure requires geometric sequencing, locking the butter into the detrempe, executing a single fold, resting, and finally completing a double fold. Over this sequence, the baker must systematically reduce a solid 6 to 8 millimeter block of butter down to a final dough thickness of exactly 3 millimeters. A shattered, dense interior is never a random accident in the oven. It is the mathematical consequence of failing to balance temperature, pressure, and plasticity on the bench. Protecting those delicate layers means rolling evenly from the center outward. This prevents the localized compression that causes tight, closed honeycomb structures. The moment the gluten fights back and resists the pin, the rolling must stop. The dough goes immediately into the cooler to rest, preventing internal tearing. Once shaped, the final variable is proofing. The tense structure of the raw dough must relax entirely until the pastry reaches a visibly jiggly state. If it goes into the heat underproofed, those tightly wound layers will forcefully spread outward across the pan, rather than springing upward vertically. The oven cannot correct mistakes. The final bake is just the thermodynamic execution of decisions locked in long before the tray went in. The flaky golden exterior remains a deceptive facade. The absolute truth of a baker's technique is hidden inside the cross-section. Mastering lamination requires working backward, It means analyzing the final baked structure to reconstruct the exact history of how that raw dough was handled. Debugging a croissant proves a baker's ability to translate visible symptoms into invisible bench solutions. Every croissant tells the story of its creation,